Now that we understand how to write rate laws, let's apply this to a reaction. So here we have the reaction of nitric oxide, which is NO, and hydrogen to give us nitrogen and water at 1280 degrees C. In part A, our goal is to determine the rate law. And from the last video, we know that the rate of the reaction is equal to K, which is the rate constant, times the concentration of nitric oxide, right? So nitric oxide is one of our reactants. So the rate of the reaction is proportional to the concentration of nitric oxide to some power x, right? We don't know what x is yet. We also know the rate of the reaction is proportional to the concentration of our other reactant, which is hydrogen. So we put hydrogen in here, but we don't know what the power is, so we put a y for now. All right, we can figure out what x and y are by looking at the data in our experiments. So let's say we wanted to first figure out what x is. Right? So to figure out what x is, we need to know how the concentration of nitric oxide affects the rate of our reaction. So we're going to look at experiments 1 and 2 here. And the reason why we chose those two experiments is because the concentration of hydrogen is constant in those two experiments. The concentration of hydrogen is 0.002 molar in both. So if we look at what we did to the concentration of nitric oxide, right, we went from a concentration of 0.005 to a concentration of 0.010. We increased the concentration of nitric oxide. We increased the concentration of nitric oxide by a factor of 2. We doubled the concentration. What happened to the initial rate of reaction? Well, the rate went from 1.25 times 10 to the negative 5 to 5 times 10 to the negative 5. So the rate increased by a factor of 4, right? We increased the rate by a factor of 4. And if you have trouble doing that math in your head, you could just use a calculator, right, and say 5 times 10 to the negative 5. And if you divide that by 1.25 times 10 to the negative 5, this would be 4 over 1, or 4. So this rate is 4 times this rate up here. Now we know enough to figure out the order for nitric oxide. Because remember from the previous video, what we did is we said 2 to the x is equal to 4. So over here, 2 to the x is equal to 4. Obviously, x is equal to 2. 2 squared is equal to 4. So we can go ahead and put that in for our rate law. So now we know the rate is equal to K times the concentration of nitric oxide. All right, this would be to the second power. So the reaction is second order in nitric oxide. Next, let's figure out the order with respect to hydrogen. So this time we want to choose two experiments where the concentration of nitric oxide is constant. So that would be experiments 2 and 3, where we can see the concentration of nitric oxide has not changed. It's 0.01 molar for both of those experiments. But the concentration of hydrogen has changed. It goes from 0.002 to 0.004. So we've increased the concentration of hydrogen by a factor of 2. And what happened to the rate of reaction? We went from 5 times 10 to the negative 5 to 1 times 10 to the negative 4. So we've doubled the rate. The rate has increased by a factor of 2. And sometimes the exponents bother students, right? How is this doubling the rate? Well, once again, if you can't do that in your head, you could take out your calculator and take 1 times 10 to the negative 4 and divide that by 5 times 10 to the negative 5, and you'll see that's twice that. So the rate goes up by a factor of 2. So now we have 2 to what power, right? 2 to what power is equal to 2. So 2 to the y is equal to 2. Obviously, y is equal to 1. 2 to the first power is equal to 2. So now we know that our reaction is first order in hydrogen. So we can go ahead and put that in here. So we can put in hydrogen, and we know that it's first order in hydrogen. So we've now determined our rate law. In part B, they want us to find the overall order of the reaction. And that's pretty easy to do because we've already determined the rate law in part A. We know that the reaction is second order in nitric oxide and first order in hydrogen. So to find the overall order, all we have to do is add our exponents. 2 plus 1 is equal to 3. So the overall order of the reaction is 3. Let's compare our exponents to the coefficients in our balanced equation for a minute here. So it's very tempting for students to say, oh, we have a 2 here for our coefficient for nitric oxide. Is that why we have a 2 down here for the exponent in the rate law? But if you look at hydrogen, hydrogen has a coefficient of 2, and we determined that the exponent was a 1 down here in the rate law. So you can't just take your coefficients in your balanced chemical equation and put them in for your exponents in your rate law. All right, so you need to look at your experimental data to determine what your exponents are in your rate law. And later we'll get more into mechanisms, and we'll talk about that a little bit more. All right, let's move on to part C. In part C, they want us to find or calculate the rate constant K. Well, we could calculate the rate constant K by using the rate law that we determined in part A, and by choosing one of the experiments and plugging in the numbers into the rate law. So it doesn't matter which experiment you choose. You could choose 1, 2, or 3. I'm just going to choose 1 here, so experiment 1. And we're going to plug all of our information into the rate law that we just determined. For example, right, in our rate law, we have the rate of reaction over here. Well, for experiment 1, the initial rate of reaction was 1.25 times 10 to the negative 5. And it was molar per second. So we're going to plug this in. We're going to plug this in to our rate law. So let's go down here and plug that value in. 1.25 times 10 to the negative 5, and this was molar per second. All right, so that takes care of the rate of the reaction. Next, we have that equal to the rate constant K, so we're trying to solve for K, times the concentration of nitric oxide squared. So let's go back up here and find the concentration of nitric oxide in the first experiment. The concentration is 0.005 molar, right? So we're going to plug in 0.005 molar in here. So we have 0.005 molar. And next, we're going to multiply that by the concentration of hydrogen, right? The concentration of hydrogen to the first power. So we go back up to experiment 1, and we find the concentration of hydrogen, which is 0.002 molar. So we plug that in. So we have 0.002 molar. Next, all we have to do is solve for K. So let's go ahead and do that. So let's get out the calculator here. And we could say 0.005 squared, right, gives us 2.5 times 10 to the negative 5. We need to multiply that by 0.002. So on the right side, we would have 5 times 10 to the negative 8. Right, so we have 5 times 10 to the negative 8. Think about your units, right? This would be molar squared times molar over here. So molar squared times molar, right? And all of this times our rate constant K is equal to 1.25 times 10 to the negative 5, right? Molar per second. Let's go ahead and find the number first, and then we'll worry about our units here. So to find what K is, we just need to take 1.25 times 10 to the negative 5, and if we divide that, right, if we divide that by 5 times 10 to the negative 8, then we get that K is equal to 250. Right, so K is equal to 250. We can go ahead and put that in here. K is 250. What would the units be? Well, we have molar on the left, we have molar on the right, so we could cancel one of those molars out. And so on the left we have 1 over seconds, and on the right we have molar squared. So we divide both sides by molar squared, and so we get for our units for K, this would be 1 over molar squared. This would be 1 over molar squared times seconds. And so we found the rate constant for our reaction. And notice this was for a specific temperature, right? So our reaction was at 1280 degrees C. So this is the rate constant at 1280 degrees C. Finally, let's do part D. So what is the rate of the reaction when the concentration of nitric oxide is 0.012 molar and the concentration of hydrogen is 0.006 molar? Well, we can use our rate law, right? So our rate law is equal to what we found in A, right? Our rate law is equal to K times the concentration of nitric oxide squared times the concentration of hydrogen to the first power. So our goal is to find the rate of the reaction. So we're solving for R here, and we know what K is now. K is 250, 1 over molar squared times seconds, right? So we have that. The concentration of nitric oxide is 0.012, so we have 0.012, right? This would be molar, and we need to square that. And then, so all I did was take this, right? I took this and I plugged it into here. And now we're going to take the concentration of hydrogen, which is 0.006 molar, and plug that into here. So let's go ahead and do that. So that would be times 0.006, right, molar. Let me go ahead and put in the molar there. So 0.006 molar to the first power. And we solve for our rate. So the rate is equal to, let's do the numbers first. So we have 0.012 squared, 0.012 squared, right? And we're going to multiply that by times 0.006, and then we also need to multiply that by our rate constant K, so times 250. And this gives us our answer of 2.16 times 10 to the negative 4. Let's round that to 2.2. So we have 2.2 times 10 to the negative 4. And in terms of our units, right, if we think about what happens to the units here, we would have molarity squared, right here, molarity squared, so we end up with molar per second, right, which we know is our units for the rate of reaction, so molar per second. So we found the rate of our reaction.